This is the pre-lab for experiment 5, where we're going to do our first of a series of experiments based upon qualitative analysis. One of the jobs of a chemist is to determine what might be in a potentially unknown sample. You may be testing a water sample supply that comes from groundwater underneath a gasoline station, and you want to know if maybe benzene has leached from the underground gasoline tank into the water supply. Or you may be working for a water district like in Flint, Michigan, and you want to determine if there's lead ions in the water there. So if you're trying to determine what is in an unknown sample, that's called qualitative analysis, qual from Spanish meaning what, correct? If you want to determine how much of something there is in an unknown sample, that's quantitative analysis, where quant, like the word quantity, is determining how much. Now, for organic substances like benzene, you'll actually go through a series of qualitative analysis experiments in organic chemistry to learn to predict whether those organic molecules are in unknown samples. But in general chemistry, we're going to learn a series of techniques to identify different cations that may be in a particular unknown sample. So if you have a water sample and you want to know what positive ions are in there, a water sample could contain any number of different cations. Every single metal has at least one cation. Many of them have several cations. And so this is a pretty daunting feat. There's lots and lots of possible cations there could be in a water solution. And if you're working in Flint, Michigan, and you want to try to see qualitatively if there are lead-2 ions in that water sample, you would have to try to come up with a reaction that would do something that lead would do, but the other ions wouldn't. Now, lead ions are actually insoluble with chlorides, bromides, or iodides. So if you added chlorides, bromides, or iodides, you would get the lead to precipitate out, but other things precipitate out as well, silver ions and mercury 1 ions, for example. So precipitation wouldn't necessarily show that lead is present. You could make lead precipitate out with carbonate ions, but that actually precipitates out 20, 30, 40, 50 other cations. So a technique used to determine qualitatively what's in a sample is to take the potentially large amount of cations, and I've got maybe 20 or so listed across the slide here, and break them down into smaller, manageable groups. And then each of those groups, you try to separate the cations from each other and then provide a test to prove whether they're present or not. So we're going to actually break down all the possible cations into 5 what are called qualitative groups. And this experiment number 5 is going to be based upon the qualitative group number 1. And the way you separate out a small number of these cations from all the rest is by using a precipitating agent. So therefore only a few of them precipitate out. You take that precipitate and then you analyze that. So the qualitative cations are the ones that will precipitate out if you add hydrochloric acid. Hydrochloric acid ionizes into hydrogen ions and chloride ions. The hydrogen ions have essentially no effect on cations, but the chloride ions do. As we had just mentioned, chloride ions will precipitate with silver ions, mercury 1 ions, or lead 2 ions. So if we add hydrochloric acid and get a precipitate, we know there's either silver, mercury 1, lead 2, or a combination of those that's in our unknown sample. So if we try to graphically represent what we're doing in a qualitative analysis scheme, we draw a flow chart. And I have the flow chart started here. At the very top are all the possible cations that may be in our unknown sample. What's our first step? Our first step is to add 6 molar hydrochloric acid. Now, if the hydrochloric acid or whatever reagent we're using causes some cations to precipitate out, I'm going to draw a bracket. And on the left side of the bracket, I'm going to tell what would precipitate. And on the right side of the bracket, I'm showing all the cations that do not precipitate. So if I added hydrochloric acid to a solution containing all of the cations above, we would precipitate out silver chloride, mercury 1 chloride, and lead 2 chloride, but every other cation after that would remain in solution. Our experiment today will be taking that white solid, which will contain either silver chloride, mercury 1 chloride, or lead 2 chloride, or a combination of all 3, and try to determine which of those are present in an unknown. And in our experiment, we'll actually do a known sample that actually has all 3, so you'll be able to see what the results you get from each of the steps in the procedure, and then you apply the same procedural steps to an unknown to try to identify which one of those are present. Now, on the right side of this bracket are all the ions that did not precipitate with hydrochloric acid. We're going to discard those today because we're not going to be testing for any of those. We're only going to learn how to identify and separate silver ions, mercury 1 ions, and lead 2 ions. But if we were to take that solution on the right side of the bracket and try to then select out a smaller subset of cations, we'll do that with a second precipitating agent. And the second precipitating agent we would use would be one that produces sulfide ions in an acidic solution. And so hydrochloric acid is used to make the solution acidic, and then an organic substance, thioacetamide, which if you heat it up decomposes to produce hydrogen sulfide gas, which the sulfide ions therefore will precipitate some of the cations here. In an acidic solution, the thioacetamide will provide enough sulfide ions to precipitate out tin 4 sulfide, copper 2 sulfide, antimony 3 sulfide, and bismuth 3 sulfide. So we've now broken down the remaining cations to a smaller subset, and that black solid of SNS, CuS, Sb2S3, and Bi2S3 can now be analyzed for each of the individual cations, and that particular experiment will be our experiment based upon qualitative group 2. Those cations make up qualitative group 2. What's on the right side of the bracket are all of the cations now that did not initially precipitate with just HCl and did not precipitate with HCl with thioacetamide. If I take this solution, I continue to add thioacetamide to it, but I adjust the pH from acidic to basic by adding ammonia and ammonium chloride. I'll actually get another subset of those cations to precipitate. I'll precipitate out iron 3 as iron 3 hydroxide, cobalt 2 as cobalt 2 sulfide. I'll precipitate out nickel 2 sulfide, aluminum hydroxide, and zinc sulfide. Those particular cations that have precipitated out with thioacetamide in a basic solution are what we call the qualitative group 3 cations, and our third qualitative analysis experiment this semester will be to separate and analyze for those 5 different cations in that group. The final set at the very right, barium ions, calcium ions, magnesium ions, sodium, potassium, and ammonium. Those make up groups 4 and 5, and our final qualitative analysis experiment will be to analyze and separate each of those to show if they're in a solution or not. So we're only going to deal with, in experiment 5, group 1 qualitative analysis group cations, which are silver, mercury, and lead. So we're going to actually add hydrochloric acid to an unknown water solution. If we get a precipitate, we'll then analyze that precipitate to see if it contains either silver ions, either mercury 1 ions, either lead 2 ions, or a combination of any 2 or 3 of those. So in our experiment today, the first step is going to be to separate out the group 1 cations from all the other possible cations that may be in the solution. So pictorially, if I have a test tube that contains an unknown water sample, and I'm trying to determine what cations are in that, the first step I'm going to do is I'm going to add hydrochloric acid to see if I get a precipitate, because if I do, that means I would have to have either mercury 1, lead 2, or silver ions in there. So if this is a known solution, then it would contain all the different cations we listed on the previous slide. So we would know that silver ions, mercury 1, and lead 2 ions are in there. And I'm going to then draw a flow chart representing the procedural steps we're doing here in this particular experiment. So the first step, add 6 molar hydrochloric acid. The chloride ions will bond to any silver ions, mercury 1 ions, or lead 2 ions that are in there and create a precipitate. And if you take that test tube and put it in a centrifuge and whirl it around, you're going to pack the solid at the bottom, and it's going to be very clear that you're going to see you've now separated this into a solid phase and a liquid phase. So the solid at the bottom will be silver chloride, mercury 1 chloride, and lead 2 chloride if it's a known solution. If it's an unknown solution, it can be any 1, 2, or 3 of those. The top solution there is going to be all the ions from groups 2, 3, 4, or 5 because they don't precipitate. And now we can manually separate these 2 groups of cations. I'm going to stick a capillary pipette into the test tube. I'm going to suck out all the liquid and transfer it to a different test tube. That different test tube will now have the solution of group 2, 3, 4, and 5 cations, and my original test tube has my precipitate in it. That's the test tube I'm going to deal with, the white solid that contains potentially 3 different cations that have precipitated out. So on my flow chart, the way I would represent this is I would take the original solution, which is written at the top. It has silver, mercury 1, lead 2 ions, and all the other cations to groups 2 to 5. I add hydrochloric acid, and because it splits it up into a solid and liquid phase, I bracket it. On the left side, I write the solid phase. So in this case, that's going to be the silver chloride, mercury 1 chloride, lead 2 chloride. And on the right side is the liquid phase. That's going to be the solution of all the cations that did not precipitate. And in this particular lab, we're not going to deal with the solution that has the group 2, 3, 4, 5 cations in it. And so we're going to discard it. If we were going to analyze for the other cations in successive periods, then we would save those. But right now, we're going to discard that. We're only going to experiment with the white solid we create. So let's go to step 2. What are we going to do with this white solid? Because each of these have precipitated out, they're all clumped together. We can't analyze for any one of them. We have to find a way to separate them. And in group 2, the way we're going to do that is by adding hot water. When we add hot water to this precipitate, what will happen is that the hot water will interact with one of those solids. And to make sure it does, we're going to put this in a hot water bath and let it sit there for a while. And you're going to see possibly the amount of solid decrease because one of those precipitates happens to be soluble in hot water, and that one is lead 2 chloride. So if lead 2 chloride is present, some of the precipitate will dissolve, and the lead 2 chloride will dissociate into ions so that the solution above now will have lead 2 ions in it, but the silver chloride and the mercury 1 chloride are not affected by the water temperature going up. They're going to remain as solids. I've now separated the lead ions out from the silver chloride and the mercury 1 chloride. To physically separate them, we would put this in a centrifuge to pack down the solid. Then I would use a capillary pipette to suck the liquid out. And I now have in the bottom left-hand corner my solution that contains the lead 2 ions. And in my original test tube, I have the solid that contains the silver chloride and the lead 2 chloride. On my flow chart, I would now write a line next to it written hot water. That's the reagent I'm using, and the hot water now causes my white solid to separate into 2 phases. On the left side is going to be the solid phase. That's going to be the silver chloride and the mercury 1 chloride white solid. But on the right side is going to be a colorless solution, and that's where the lead 2 ions would wind up going. Now, what if you didn't see a white solid? What if all of your precipitate disappeared and you have no solid? All you have is a colorless solution. If your unknown does that, quite often that causes students to panic because they think they've done something wrong. But in all reality, what this has done is it made your life incredibly easy. That just means your unknown could not have any silver or mercury 1 ions in it, because if it did, you would still see a precipitate there. So instead of being panicked by not having the solid here produced after the hot water, you should rejoice because that actually means the only possible ion you could have in your solution would be the lead 2 ions. Now, how do we know we have lead 2 ions in there? Well, what does the solution look like? It looks like a colorless solution. So that's really the problem in Flint, Michigan, right? I mean, if you have pure water or water that has lead ions in it, you can't tell there's lead ions in there. We haven't proven there are lead ions in there. You have to do something to verify that that colorless solution is not pure water, but actually has lead ions in it. So what we're going to do is we're going to go to step 3 now, and we're going to take the colorless solution, and we're going to add something to it that would react with the lead 2 ions if they're present. And the reagent we're going to use in step 3 is 1 molar potassium chromate with the solution made acidic with some acetic acid. Now, lead 2 ions will precipitate with chromate ions, and so when you do this, you will get a yellow precipitate if lead ions are present. If the lead ions aren't present, you'll just get a yellow solution because the potassium chromate solution is yellow. It's going to make the solution turn yellow whether lead's there or not. But if you put this in a centrifuge, you'll see if there's a yellow solid at the bottom, the only thing that yellow solid can be would be lead 2 chromate. So if you see this, that means lead is present. So on the right side for our flow chart, to graphically show what we're doing to the colorless solution, we're adding potassium chromate and acetic acid to it, and it's going to separate that solution into a solid and liquid phase. So I'm going to bracket it. On the left side is going to be my solid. That's going to be PbCrO4, and on the right side is going to be a yellow solution with no particular chemicals in it. It would have excess chromate ions. And if you see that yellow solid there, that proves that your unknown must have had lead in it. There's no other way you would get a yellow solid if lead wasn't present. Now, what happens if you add the potassium chromate and you get a lovely yellow solution, but you don't get a lead solid? Well, that just means there was no lead ions present. So that's a possibility for your unknown, but when they do the known solution, because all the cations are present, you will definitely see a yellow solid here. So that's the first cation we have learned to specifically identify in our entire qualitative analysis scheme. You will first identify whether lead is present or not. And now once we've done that, we can now go back to the white solid that we put aside that contains either silver chloride, mercury 1 chloride, or a combination of the two, try to separate those and prove whether silver or mercury or both are present. So this is step 4. So now we don't have to deal with the colorless solution anymore that's now become yellow. We can throw that away. We're only dealing with the white solid that we had saved from step 2. So this white solid, which can contain silver chloride or mercury 1 chloride or both, we're going to add to it a reagent of ammonia. And ammonia is a base. And as it drips in there, what ammonia does is ammonia molecules, not because they're a base necessarily, but what they do is they actually bond to silver ions to form a very stable complex ion whose formula is Ag, NH3 taken twice with a positive 1 charge. And that bond is so strong that the ammonia molecules will find the silver ions in the precipitate, pull them out of the precipitate, bond to the ammonia, and you'll actually dissolve the silver ions as Ag, NH3 taken twice positive. So by adding ammonia, that silver chloride precipitate will dissolve because a very stable complex ion is being created. And then the ammonia does a second thing. It reacts with the mercury 1 chloride, and the mercury 1 chloride undergoes a disproportionation, which just is a fancy way of saying the mercury 1 ions undergo an oxidation and reduction at the same time. The mercury 1 ions get reduced to elemental mercury with a charge of 0. That's going to appear black. And then the mercury 1 ions are going to be oxidized up to mercury 2 ions, and they're going to bond with the ammonia and some chlorides to form a white solid. So when the ammonia is added, if both are present, what you'll see is a solution at the top, and that clear solution at the top will actually contain the dissolved silver ions bonded to the ammonias in the form of Ag, NH3 taken twice positive. At the bottom, you will see a black or white or combination of the two solid, because the black would be the result of any elemental mercury, and the white solid would be the precipitate HgNH2Cl. So we've had a way now to separate the silver from the mercury by adding the ammonia. And if you then suck out the solution at the top with a micropipette or a capillary pipette, we now have separated the solution on the bottom left, which contains the silver ions in that complex form, from the black and white solid, which is our mercury. If you see that black and white solid form, that is definite proof that mercury had to be present. Nothing else will turn a black and white color when ammonia is added. So that's the proof of the second cation being present. On our flow chart on the right side, what we do under the white solid is we write a line and we write the reagent we added, which was ammonia. And the ammonia is causing now the resulting solution to turn into a solid phase and a liquid phase. So I'm going to draw a bracket. On the left side is going to be my solid phase. So that's going to be the mercury with the mercury amide chloride compound. And then on the right side is going to be my colorless solution that contains the silver ion complex with ammonia. That black and white solid, as we said, is proof that mercury must have been present. If you add ammonia and the entire solution turns colorless and you don't see a black solid, what does that mean? That means your unknown didn't have mercury in it. But if you see a black solid, that means mercury was present. So we've now learned to identify whether lead-2 ions are present or not in an unknown sample. And we've now learned how to identify whether mercury 1 ions are present or not in an unknown sample. The only thing left now is to try to determine whether the sample really had silver ions or not. And actually, there's no way to know right now because the solution we have is colorless and it looks just like water. So how would you know if water has silver ions in it or not? we need to do one more step to try to react those silver ions to make them turn into something that would only happen if silver was present. And that's going to be step 5. So we're going to take the colorless solution, and what we're going to do is we're going to add to that colorless solution that theoretically may contain the Hg, NH2, or rather the Ag, NH3 taken twice positive cation, and we're going to add nitric acid to it. I said before that ammonia was a base, and this is where that's important. Bases react with acids. So if I drip nitric acid in there, the hydrogen ions from the nitric acid will react with the ammonia molecules, forming ammonium ions, NH4 positive. Ammonium ions don't bond to silver ions, so therefore we remove all of the ammonias from the silver complexes, freeing up the silver ions. If the silver ions are floating around in the solution, you remember what we added to the solution way back in step 1? We added a bunch of hydrochloric acid. So there's chloride ions in there. So if the silver ions are now freed because all the ammonia molecules have been turned into ammonium ions, so the complex ion can't exist, the silver ions will eventually bump into the chloride ions, and you will see a white precipitate form. If you do, the only possible thing that can be would be silver chloride, because we've already removed all the lead, we've already removed all the mercury. The only ion that could precipitate with those chlorides in there would be the silver. So in our flow chart, the final reagent we're going to add is going to be nitric acid. The hydrogens react with the NH3s to form NH4s, so therefore the silver ions have been freed up to bond with chlorides that were originally placed into the solution. So if you see a white solid now formed, that means silver ions must have been present. If you don't see a white solid, that means silver was not in the unknown, but if you do, then it is. And in the procedural steps to actually verify this, what you're going to do is you're going to then add a little bit more ammonia to this. And if you add enough ammonia, you can actually cause the ammonias to react with the silver in the silver chloride, and they reform the complex ion. You're going to make the precipitate disappear. And then if you add a bunch of nitric acid back to this, you're going to react away all the ammonias you put in there, and you'll make the precipitate come back. So just an additional test to verify that was really there. And so that would give you the white solid silver chloride. So this is what experiment 5 is going to be. It's going to be the complete analysis and separation of the group 1 cations. We'll learn how to do that. And then as we progress through each of the qualitative groups, we're going to precipitate out a small subset of cations. And once we've done that, we will learn the procedural steps that separate each cation and then what reagent we would have to add in order to prove they're actually present.